This is really nice. Oh, you ready? Okay, so this is a quick review about energy diagrams and the types of energy we've discussed so far. So an energy diagram is like one of these things, kind of showing the relative energies of different points along a reaction pathway. It's also called a reaction coordinate diagram. Coordinate. So what does it show? Well, it can show the activation energy of a reaction. It can show the heat of reaction, delta H, and then also possibly some other pathways that a reaction takes. So it's just this plot of energy versus points along the reaction pathway. And that certainly includes the beginning point, reactants, and the final point along the reaction pathway, the products. And in the middle, there's got to be at least one transition state. And that's that high point, high energy point on the reaction. And if you want to know about the activation energy of reaction, you're simply going to look at the energy of reactants and then the highest point. So it's really the difference between reactant energy and transition state energy. So on this graph, I have a 10 here and a 70 there. So the difference there, that whole amount of energy for collisional events needed to start the bond breaking process, it's going to be 60 kilojoules. And this pathway that I've drawn shows the products that are less stable than reactants. So products higher in energy, they're at 30, reactants are 10. So that means final minus initial, products minus reactants, gives us a positive 20 kilojoules for the delta H. So that shows us an endothermic pathway. Now over here, I have sketched just what you would see as an exothermic pathway. So the reactants here are less stable. They're higher in energy than the products. And so in this pathway, the final state minus the initial state is going to give us a negative number. That's exothermic. And activation energy here is still the same. It's the difference between reactants and transition state, always between reactants and transition state. So it's this quantity. I don't have any numbers here. So if activation energy is only the difference between reactants and transition state, here's a question. What if we looked at this reaction in the reverse direction? So in the reverse direction, we'll treat the products as the reactants, the starting point, and then the reactants as the products, the final point. In the reverse direction, the difference in energy between the products and the transition state would be, let's write that in there, activation energy for the reverse reaction. Well, that's going to be the 70 minus the 30, that's 40 kilojoules, 40. So in the reverse direction, we have a lower activation energy than we do in the forward direction, which is 60. Interesting. Reverse direction. I wonder how we'll later describe something about reversible reactions. Now, last class, we talked a little bit about catalyzed pathways. So a catalyst is a substance that will participate with the reactants, weaken some key bonds. And so the amount of energy needed to activate the reaction is going to be reduced. So it's a different pathway. So let's say I'm sketching in a pathway here where the high point, this transition state, only gets up to about 50 compared to the 10 we start with. So in that case, this activation energy of the catalyzed pathway is just 40 compared to 60. Yeah, in the forward direction, this catalyzed pathway definitely is a little bit easier. The lower the activation energy, the faster the reaction. And so an inhibitor then, that's going to be quite different. Let's see, I got purple for that. So if we have an inhibitor pathway, Then we're going to say, hey, that's going to raise the activation energy. So instead of 10 to 40 or 10 up here for a 60 kilojoule activation energy, an inhibitor would require a pathway where we have something higher. So the purple now would represent an enormous activation energy, much higher than either the regular pathway or the catalyzed pathway. So inhibitor. So sometimes we want to slow reactions down by building something that'll react so strongly with reactants that the collisional events will have to require so much energy. Most of those collisions will be unsuccessful, and that slows down the reaction. So there's a lot we can learn from this diagram. Now there's some other pathways besides catalyzed and inhibited pathways we could draw in. Because essentially I've drawn a very simplistic diagram. We can realize that there's a lot of reactions that instead of just kind of going from a reactant to a transition state to a product, sometimes we see things where we have a reactant to a transition state, and then before it gets to products, it kind of forms something else, and then another transition state, and then maybe products. Look at that. That's a different pathway. Activation energy would still be this difference between reactants and this first transition state. And delta H is still the difference between the products and the reactants. But what else is going on? We've got this other sort of point here and another transition state. This point is not a reactant or a product, and at some point along the reaction pathway. So we need a new name. This is going to be called an intermediate. It's kind of a minimum there as opposed to a maximum. So this is something that's stable. Maybe it exists, whereas a high energy, it doesn't exist at all. It's like a pass-through state. This is a little bit of a lifetime, but see, it's very unstable. It's much higher in energy than reactants and products. And then this is just like a pass-through state, and then this is the final state. We'll learn more about intermediate states